Let us look at an AP Physics C mechanics question from 1991. And we're going to be looking at a kind of a pulley problem slash a torque problem. A little bit of moments of inertia tucked in, and a little bit of energy as well. Now, this mechanics problem comes from 1991, like I said, which means that they were written a little bit differently at this point in time. That was pretty much 30 years ago from where we're currently at when this video is made in 2020. So it might look a little bit different, but all the physics concepts are definitely still the same. So let's take a look at what we got here. What we have are two masses, M1 and M2, and they are connected by light cables, which means the cables themselves are massless, to the perimeters of the two cylinders of radii R1, so this is R1 here, and R2, which goes out like that. The cylinders are rigidly connected to each other, and by cylinders they're talking about the two kind of discs that are around that pivot, but are free to rotate without friction on a common axle. The moment of inertia of the pair of cylinders, so the moment of inertia of the pair of cylinders is 45 kilogram meters squared. We know that R1 is 0.5 meters, and R2 is 1.5 meters, and mass 1 is 20 kilograms, okay? And the way this is kind of set up is that mass 1 is kind of pulling on this side of things to cause a rotation like this, and mass 2 is pulling on this side of things to cause a rotation in the opposite direction, okay? What we are trying to do is we are trying to determine what is the mass of M2 such that the system will remain in equilibrium. Now, if you're not really thinking, you just might say, hey, it's got to be 20. If 20 is pulling this system and causing it to rotate in one direction, then 20's got to be acting on the other. And that's immediately going to send you down the wrong track. It can't be equal to 20 because of the idea of torque. Remember, a torque is a moment arm crossed with a force, which really means that this is RF sine of theta. In our case here, we're going to ignore the sine of theta because everything's acting at 90 degrees, which makes sine of theta 1. But our moment arms are different here. We've got a moment arm of 0.5 meters for R1 and a moment arm of 1.5, or 3 times as much, for R2. So what we can do is this. We know that since these torques are acting in opposite directions, one's going counterclockwise, one's going clockwise, we know that the sum of the torques have to equal 0 to be in a static equilibrium position. What this means is that the torque from block 1, M1, and the torque from block 2, M2, have to be equal, and they have to work against each other. A way of writing that would be something like RF1, and I'll call counterclockwise here. I'll call that the positive direction. So I'll call this up here a positive torque, and I'll call this a negative torque. But this allows me to say that RF1 minus, well, this is R1, minus R2 F2 equals 0. Which means I can set these equal to each other. I can say R1, F1 is the weight pulling down, so this is M1G. That has to equal, by moving this quantity to the other side, R2 M2G. And at this point, I'm just solving for M2. The G's divide out, which is nice, and I get that R1 over R2 times M1 equals M2. In this case, R2 is 0.5, R1 is 0.5, R2 is 1.5. So I'm going to get 0.5 over 1.5 times 20 kilograms equals M2. And that's a third of 20. So M2 should be something around, well, whatever 20 over 3 is. I don't care. Doesn't matter. We can leave it in a fractional form. Easier. Okay? So that's it. That's what we get for M2 there. And it's just the idea of torques. The important thing for us. For For the second and third part, B and C, we're actually going to see that these are interconnected parts of the problem. Mass 2 now is removed from the system, and then the system is released from rest. So what's going to happen is, if we take a look up here, mass 2 is going to go away, and in doing so, we are only going to have one torque exerted on our system from mass 1. So what we are looking to do here is two things. We're looking to determine the angular acceleration of the cylinders, which, remember, angular acceleration is an alpha. And we're also looking for the tension in the cable supporting M1. So we're looking for alpha, or how quickly this system is accelerating in an angular direction. And then we're also looking here for what is the tension in this cable. Okay, and remember that tension is technically in both directions here, depending on how we want to think about it. It's equal and opposite, but there's a tension there in that cable. So that's what we were asked to do in parts B and C, and we're going to quickly see that these are tied together. Okay, so what we can do here is, if we would like to find some angular quantities, we have to look at rotational quantities as well. Angular quantities and rotational quantities go together. So if we want to do angular acceleration, we need to start looking at the torque. And we know that torque equals, just like F equals ma, torque equals I alpha. I being that moment of inertia, how difficult it is to get an object to begin to rotate and to accelerate its rotation. So in this case, we only have one torque. We only have the torque from the mass going down, M1. So we can just call this RF1 here, which is just R1 times M1 times G. And that has to equal the moment of inertia of the entire double pulley system, which for us is the 45 kilogram meters squared, and then times alpha. Okay, so that's what we have going on right there. Now, oh, how do I actually want to draw this? That's not entirely true, is it? This isn't entirely true. This force right here, let's draw this picture. There's the disc. There's the rope, like that. And then here is the block down here. Let's make the block blue. And the block is being pulled up with a tension and down with a weight. When I look at just my wheel though, this is the tension. I don't know what that tension is. That tension is not equal to the weight into this problem. So I cannot just say that that force is equal to mg. I just have to call this R1 times the tension on that block. I don't know what it is. Okay. So this is where we're at right now. I would like to solve for this alpha, but I can't. I know R1 is 0.5 meters, but because I have two unknowns here, the tension and the alpha, this problem is not solvable. Which means let's look at part C. In part C, we're looking for the tension in the supporting cable. And if I get the tension in the supporting cable, I can plug it back in. So now let's go down and look at the cable scenario. When we look at the cable scenario, we're using Newton's laws because we're just looking at forces here. And we've got two forces going on here. We want to write Newton's second law, F equals ma. Anytime you're given an opportunity to write that, always write it. It'll always get you a point. And from there, we need to choose directions as positive and negative. Previously, we kind of took going counterclockwise as a positive direction, and we want to look at this torque as being like a positive quantity. So I'm actually going to make the weight pulling down positive and the torque going up negative. And in doing so, what I'll find is that the weight minus the tension has to equal ma. And the mass in this case that we're looking at in this free body diagram is mass 1, and there's the acceleration. So what we can now say is that m1 times g minus the tension equals m1 times a. Now, something that can be a little bit tricky is if we solve this for t, we're going to find that, we're going to find that t is going to equal m1 times the quantity g minus a. I just pulled this ma here over the other side, I pulled the tension over, and then I factored out an m1. Now an issue here is that when I'm looking at this problem, I'm trying to solve for tension so I can put it back up here, but I don't know what this acceleration is. That's an unknown as well. Luckily for us though, we know a workaround. Because this is all moving as one system, what we can say is that the linear acceleration of an object, that is equal to an angular acceleration multiplied by that radial distance that it's acting at. So what we can say here is that the tension equals m1 g minus, and we can put in alpha times r1. This is really nice because what this will allow us to do is, even though I can't solve this directly for t, I know t is equal to a bunch of constants, m, g, r, and an alpha term, which I actually have above. What this will allow me to do is it will allow me to substitute this term back in for tension, and now I only have one missing variable, the alpha. So what we can do now is we can say, looking up into the earlier part of the problem, we can say that, and this is just all the math that goes on here, we can say that R1, well here, let's just write this out in completeness. We can say R1 times the tension, which is this term right here, M1 times the quantity G minus alpha R1 equals, and that's going to be 45, the moment of inertia, times alpha. If we go ahead and plug in some quantities here, kind of working through this math, we're going to get 0.5 times 20 times 9.8 minus 0.5 alpha equals 45 alpha. Let's just get rid of this 1/2 by dividing by 1/2 on each side. When I divide by 1/2, I'm going to multiply the 45 by 2. So I'm going to get a 90 over here. What I then can do is I can divide each side by 20, so that I now have 9.8 minus 0.5 alpha equals, well, 90 over 20, I can get rid of the zeros. That's like 9/2 alpha. And I can rewrite this 0.5 alpha as 1/2. So if I have 9/2 alpha on that side, I can add a 1/2 alpha to each side. This gives me that 9.8 equals 10 over 2 is 5, so 5 alpha. And this would have been nicer if I just chose G as being about 10, because then my answer would be about 2. But when I divide each side by 5 at this point, we find that alpha is whatever 9.8 divided by 5 is. It's about 2 rads per second squared. Okay, so that's not that bad, but it is important that in this type of problem, we actually had two things going on here. We needed to do this for torque, which was super important because we actually didn't know what this force was here. That is the tension pulling down on the pulley. Then we had to do this for F equals ma, and now that we had two equations, we can go and solve for our two unknowns. That actually just gives us the alpha here, which is part B. We actually still need to go get the tension in the cable, which is something a lot of people forget to do. This actually isn't bad to do though, because all you need to do now to get that tension is, since you know what alpha is now, you can just solve for tension. So what we can do here is we can just go back and say that 0.5 times tension equals 45 times 2. This means that tension equals 90 times 2 when I divide by the 0.5, which means the tension is equal to 180 newtons. Going back and resolving that is something that people always forget to do. They always forget to go back and do that whenever they're asked. So be careful there. Okay. And last but not least, we're asked to determine the linear speed of M1 at the time it's descended 1 meter. So when M1 has fallen down 1 meter in height, how fast is it going at that point? There are a few ways to do this. My personal favorite is with energy. If this is starting at rest, we can say that the mechanical energy is 0. And that means when this mass falls 1 meter, we can say its gravitational potential energy that it had, mgh, or 20 times 9.8 times 1 meter, has to be equal to the kinetic energies that it now has in the system. And the kinetic energies are 1/2 mv squared for the mass itself falling, but it also has a rotational kinetic energy because those two cylinders are tied together and they are rotating as well. So that's going to be 1/2 I omega squared. So at this point, that is the equation that we can use there. It's a nice, easy, quick thing to do. One of the things that we might have to recognize, though, is that when we are looking at this, it is easier to look at omega squared as the fact that omega equals v over r. So we could rewrite this as 1/2 mv squared plus 1/2 I v squared over r squared. And what this allows us to do is, because there's v squareds in both terms, I can pull that v squared to the outside. So what I now have is 1/2 v squared times the quantity m plus I over r squared. And the r squared we have in this is r1, because that is where this pull is being acted on. And at that point, we just need to plug in some values and solve this for v. I guess on the left side, 20 times, let's just say about 10. That's 200. So I'm going to get 200 on that left side, right? Well, let's just leave this as mgh. It'll make life easier. We'll go back. Numbers are the worst. So this is just mgh. So now if we solve this, I'll bring the 2, or the 1/2, I'll bring that up. So I'm going to get 2 mgh. And then this entire term here, I need to divide by that. So divided by the quantity of m plus I over r1 squared. That's going to equal to v squared. And then that means I need to take a square root of the whole thing to get an answer. And plugging in some numbers here, let's see, this will be the square root of 2 times 20 times, let's just say g is 10, times 1, all over 20 plus 45 over the quantity of 0.5 squared. And you throw that through a calculator, and you should get a value of around 1.4 meters per second. Our numerator here will be about 400. And our denominator, if I'm looking at this correctly, 0.5 squared will give us 0.25, and then 45, a quarter of that's 11 and a little bit, so plus 20. So 400 divided by that gives us about 12. Wait, did I mess up a number somewhere? 2 times 10 is 200 times 2 is 400, right? So 400 divided by, and that's, let's see, 0.5 squared, 45 divided by, oh, okay, whoops, that's 180. This gives you 180 down here on that. So 180 plus 20 is 200, so we get 400 over 200, which is 4 over 2, square root of 2, that's an easy one. Boom. So yeah, not too bad there. Just don't mess up with the calculator like I just did. So yeah, wasn't a crazy problem. A little bit of torque going on, a little bit of rotation. Big thing to remember, and I think the trickiest part of this problem, is when you're looking for the angular acceleration, you need to understand that that is a torque acting on this diagram here. That's the torque going down here. It's not the weight, or it's the tension that's causing that rotation. It's not the weight, it's a tension there. So be careful about that one. But other than that, there's just a lot of the kind of math steps to kind of get everything, and then some energy at the end. So with that, this problem is finished. Hope you enjoyed it. Take it easy. Stop by and we'll do another one. Adios.